Okay, in section 6.4, we start by looking at this theorem that says each diagonal of a rhombus bisects two angles of the rhombus. And so to prove it, we take a look at a rhombus. Remembering the definition of a rhombus is a quadrilateral with four congruent sides. We also recognize that a rhombus is always a parallelogram as well. And we'll call that rhombus ABCD. And then we want to draw in, and we're just going to pick one of the two diagonals. It's arbitrary how we're picking them, which means we only have to prove it for one of the two of them. But we want to prove that BD bisects both angle ABC and angle ADC. And so we start with saying ABCD is a rhombus. That's our given in this theorem. And then what that tells us is that by definition, all four sides are congruent to each other. So we kind of get this extended congruence statement. And that's just by definition of a rhombus. And then we recognize that means that, oh, wait a second, I've already got two of the three sides of these two triangles, so I can prove these two triangles congruent if I claim that the diagonal is congruent to itself by reflexive property. And that allows us to prove that these two triangles are congruent. Now, normally, when we do parallelogram theorems, we often say that triangle ABD is congruent to CDB in that order. But in this case, we don't want to do that because that order doesn't give us what we need, which is to have congruent angles that are at the angle that's being bisected. So instead, because it's a rhombus and this is the same as this and this is the same as this, then we can say that triangle ABD, and it actually doesn't matter the order. We can either say CBD or CDB, but we want to do CBD because that by CPCTC, and so that's just going to be side, side, side. Right, we proved all the sides congruent. And so this then is going to allow us to say that angle CBD is congruent to angle ABD, and angle ADB is congruent to angle CDB. And that's by CPCTC. And that's what we're trying to show. We can say then that BD bisects angle ABC and angle ADC. And that's just by definition of angle bisector. Okay, and so now we know that if we're in a rhombus, we can say that this angle is the same as that angle, and this angle is the same as this angle. Because the sides are parallel, they're also all the same. And then opposite angles in a parallelogram, which this is, are congruent to each other. So actually all four of those angles have the same measure. All right, the second one looks at a rhombus, and it says that the diagonals of a rhombus are perpendicular to each other. And so again, we're going to take a look at this. And this time we need both of the diagonals drawn in. And this says that in a rhombus, if all the sides are congruent, that it's a rhombus, then these diagonals are going to need to be congruent to each other. Or these diagonals are going to be perpendicular to each other, which means we need to show that these angles are right angles. So to do that, again, we start with ABCD is a rhombus. This time, the way we're going to do it is just by showing that this triangle is congruent to this triangle. So we only need to think about, from the definition of rhombus, that AD is congruent to AB. Right? We know that the other ones are congruent as well. But we're just going to use those two. We know that AE, so if I'm looking at those two triangles, we know that AE is congruent to itself by the reflexive property. And then the last part takes advantage of the fact that a rhombus is also a parallelogram. And so any theorem that's true about a parallelogram is true about a rhombus. And so we need to show, because we've already shown that AE is congruent to itself, AD is congruent to BD, AB. If we can show that DE is congruent to EB, then I can prove those two triangles congruent by side, side, side. And I can do that because the diagonals of a parallelogram bisect each other. And so we know that E is the midpoint of BD. So from that, we have that triangles AED is congruent to triangle AEB, right? Those are the two shaded triangles. And that's just going to be by side, side, side again. And then from there, we know that angle AED is congruent to angle AEB by CPCTC. So we just showed that we don't know that these are right angles yet, but we do know they're congruent because these triangles are congruent. We also know that combined, they make up the diagonal, or that they're a linear pair. So we can say that angle AED is and angle AEB are supplementary. So we've shown that these two angles are congruent to each other. We just showed that they're supplementary. And the reason they're supplementary is because linear pairs are supplementary. And then that's enough. Whenever you got two angles that are congruent and supplementary, then we know that angle AED and angle AEB are right angles. And that's just because of the theorem that says if two angles are congruent and supplementary, then they are right. So we showed that the angle between AC, the two diagonals, AC and BD, are right angles. And so that means that by definition, AC is perpendicular to BD. And that's just because of the definition of perpendicular. All right, the last one, the diagonals of a rectangle are congruent to each other. And so for this problem, again, we're going to draw in our rectangle here. We're talking about the two diagonals, so we're talking about AC and BD. AC being congruent to BD is not true of most parallelograms, but it is true in this one. And so the way we're actually going to prove this one is we're going to kind of pull these apart and take a look at ADC, and then we're going to take a look at triangle BCD separate from each other. And so we start with ABCD is a rectangle. That's what's given to you. And then we know that AD is congruent to BC because opposite sides of a parallelogram are congruent. We also know, so that means that this is congruent to this. We also know that DC is congruent to DC by the reflexive property. It's the same line or same segment. And then the last thing is we know that these are right angles. We know that angle ADC and angle BCD are right angles. And that is because of the definition of rectangle. From there, that's enough to say that angle ADC is congruent to angle BCD because right angles are congruent. And so then we can prove the two triangles congruent. Triangle ADC is congruent to triangle BCD. And that's by side, angle, side. And so you use side, angle, side, which then proves exactly what we were trying to prove, that the diagonals, or the hypotenuse of these right triangles, AC is congruent to BD. And that's just by CPCTC. Okay, so your three theorems here that you need to know. The diagonals of a rectangle are congruent to each other. The diagonals of a rhombus are perpendicular. Note that a rhombus has perpendicular. It is clear that a rectangle is not. Make sure you know the difference between those two. A square would be. That's the one case. And then the last one is that a diagonal bisects, the diagonal of a rhombus always bisects the angles.